All right, hey, Mr. Fortin here, and I got you on this one. Number 10, somebody put this on the parking lot here in block 7. Thank you for putting it up here. So I think you put up number 10 here before the group had actually posted the answer, and they got the answer. It looks pretty good. But we're going to look together at it together on my slides here. I'll just do it together in case this isn't quite enough. But they got it. They totally understand it. I can tell what they're doing. But if you got kind of caught up somewhere in this problem, you might have trouble figuring out what this all means here. So we will still do it all together. The answer here is approximately 63 millimeters. That's all good here. They're looking at the right things. I think it's a great diagram. I won't even draw this diagram here. But we can talk about, what kind of shape that makes. We'll talk about that in a second here, okay? First of all, a nonagon is a 9-sided regular polygon. What do we know about regular polygons? Well, they're equilateral and equiangular, right? That's the definition of a polygon. Of a regular polygon is a polygon that is equilateral and equiangular. So we know that all of these side lengths here of the 9 are going to measure 25 millimeters. Okay, so we have 25 there, not 25, and 25 here. Okay, so the key to a lot of these problems was finding isosceles triangles. You had to do that here. You had to find some isosceles. Look, there's an isosceles triangle right there. Drop an altitude, right? That's what you did in this one here. This is a 108-degree angle right there. If I drop an altitude, it's going to bisect that vertex angle of this isosceles triangle down here, thus creating a 54-degree angle, right? Because it's 108 degrees in a regular pentagon. Every angle is 108 degrees, right? We get that n minus 2 times 180 divided by 2. There's lots kind of covered there. And then you can use trig, right, to get it if I know that this is the hypotenuse. So this is going to work similar here, except these aren't isosceles triangles. It's actually a freaking trapezoid right here. We'll talk about why it's trapezoid. Okay, so let's do this one together up here in case you put down number 10. And again, it's hard to predict exactly where you're getting caught up on this one here. Okay, so points A, B, C, D are 4 consecutive vertices of a regular nonagon. So what I would do to start this problem is I wouldn't draw this whole nonagon here. Okay, I wouldn't draw the whole nonagon, but I think, right, because remember, if we keep adding sides onto a polygon, it'll look a lot like the polygons in terms of number of sides that's very close to it, okay? What am I getting at there? Well, you know what an octagon, a regular octagon looks like, right? A regular octagon, you see them all the time. You're driving, your parents are driving you around. If you're on the bus, you see them. That's right, a stop sign, okay? So a stop sign is a regular octagon. So a nonagon is not gonna look that much different. So I might just start sketching out here points A, B, C, and D by it's going to end up looking like an octagon here, but I'm just going to care about these 4 points here, and I'm going to connect the diagonal here, connecting points A and D. So let's maybe draw it out here to kind of look like an octagon. An octagon has 135 degree interior angle. So this is going to be a little bit larger than that. Who knows? So I got that. So this is point A. This is point B. This is point C. And then I'll just repeat this again. Remember that irregular polygons, sides are all the same length. Okay, so I know that this is 25 millimeters. I also know that this is 25 millimeters. And we know that the interior angles are all the same. So I'll just eyeball it and just do it again here. And then, shoop, I've done it. There, I've done it. We have the same angle there and there. And we'll connect them together. Okay, what does it look like to you? Oh, it looks like a freaking trapezoid, doesn't it? But is it? I don't know. Could we prove it? Perhaps we could, okay? So this is 25 millimeters. Okay, and then this is D here. So the key to these problems is we're in trig, right? This is section 6-7 trig. We got to find right triangles, right? That's it. Find right triangles to help you out with this one here. I can find triangles because I know through a point outside of a line, I can do this. As they did on the actual, they demonstrated for us in this slide here, excellent work there, Alvin, Amos, Nolan, Sebastian. We can introduce a perpendicular, right? Through a point outside of a line, there's exactly one perpendicular that can be drawn. That perpendicular is unique and it exists, right? We know it would have to go through points. One line would have to go through points to even be perpendicular to that, right? It exists and it's unique. And anyways, it's something I normally talk about when I do that section. I didn't have that section for you guys though. So you're like, what is this guy talking about? Okay, I do this. This is a right angle here that gets me thinking. Okay, could I figure this out maybe? Like I need to figure out part of AD. Okay, so I'm gonna mark that X. Okay, I can do the same thing over here. Okay, drop it down. Boom. There we go. And I can mark that X as well. Okay, mark that X as well. So here and here, I know that. And what jumps up to you about this? Let's check it out. What jumps up to you about this? What does this look like here? Well, this looks like here, what I got here. Let's maybe make this A, B, C, D. Let's make this E, and let's make this F. It looks, sure as heck looks like the quadrilateral B, C, F, E, looks like a rectangle. And it is. This is definitely a rectangle. Why? Well, we can talk about how we can prove it. Well, these are the two perpendiculars, right? So I have a right angle here, I have a right angle here. That's nice. If I have two right angles, these are all coplanar. All these lines are coplanar. Everything you see here is in the same plane because I'm just drawing it onto a freaking sheet of paper. And if I'm doing that, then everything we see, because it exists on a piece of paper, right? A piece of paper is a plane, right? A part of a plane, a region of a plane. But anyways, because it's all coplanar, we have BE and CF are both perpendicular to AD, right? Why? Well, we drew them that way, right? Through a point outside of a line, there's exactly one perpendicular we can draw to this line AD. Because of that, we have that theorem that tells us that in a plane, if two lines are each perpendicular to the same line, these two lines are parallel to one another. Okay, parallel to one another. So these are parallel. Okay, that's nice. Those are parallel. Oh man, how am I going to prove that this is a rectangle? I thought I had it. We don't know if these are parallel. Well, I mean, these are parallel. Oh, well, this hypotenuse is the same as that hypotenuse. I mean, these have got to be the same. These triangles have got to be the same because it's like they're in identical places. Oh, man, now I'm struggling with actually how I prove this. Oh, I could prove it to you this way. Drew perpendicular? I don't know. This is a rectangle. We just have to accept that. Oh, man, Mr. Foreign can't actually prove to you it's a rectangle. These are parallel right angles. Just parallel sides is enough here. How do I get those parallel to one another? That's it. This here, hypotenuses are the same. This I marked X, this marked. If I knew that, I could use a hypotenuse leg, but haven't really justified that those have to be the same lengths. Well, I mean, we did the same thing, and it's a regular polygon. So anyways, just accept it. I'm sorry, I could prove it better to you. Okay, so this is a rectangle. What do we know about rectangles? Well, rectangles are parallelograms. Opposite sides of parallelogram are congruent. So this here, I might start doing this in different colors. This is 25 millimeters. This is going to have to be 25 millimeters too. So some of these problems you have to go for your gut, right? Go with your gut here. I did a bad job of explaining why this is a rectangle, but I think you could be fine accepting that. Well, if this is 25 millimeters, this has got to be 25 millimeters because look, this is the same freaking thing. How I set this triangle up right here, same freaking way as that one here. And I'm having trouble proving it using like HL or using ASA or something like that. Having trouble with that here. Okay. So anyways, we got that. This is 25 meters. So the key is how do we get X? Well, what have we been studying? We've been studying right triangle trigonometry, and I have a right triangle right here. That was the whole goal of setting this one up. Okay, I have a right triangle right here. So then the question is, can we get a reference angle here? Can we get one of these acute angles? And the answer is yes. Okay, so when you see something like regular polygon problems, you got to remember every regular polygon has a particular interior angle measurement. Well, why? Regular polygons are equiangular, okay? And we got to remember the formula, okay, right? We got a formula for interior angle. Interior angle of regular polygon is this, right? N minus 2, right? The number of triangles you can set up within that triangle, within that polygon, N minus 2 times by 180 over N. Right, over N here. Okay, so they didn't show it here. They ended up with getting 50 degrees there. We're going to get that, right? Because a regular nonagon here, if we do this on out here, would be 9 minus 2 times by 180 divided by 9. That's going to be the interior, one of these interior angles measurements here, okay? What the whole thing, right? The whole thing, remember the nonagon will keep going around, right? But each of these angles in the nonagon, if I keep adding it here, right, each of these is going to be one interior angle measurement. They're all congruent to one another here. So we've got to figure out what that equals, and that's 9 minus 2. So that would be 7. Okay, 7 times by 180. Okay, so the interior angle sum is 1260. We divide that by 9, right? Because a nonagon would have 9 angles, got 9 sides, going to have 9 angles. Okay, we get 140. Okay, so all these interior angle measurements equal 140. Okay, how does that help us in this problem? Well, this is a rectangle. We're just accepting that. We're moving on with life. We see it's symmetrical. Right? I mean, like, look at these triangles. Got to be the same, right? We always have symmetry within a regular polygon. So, anyways, if we drop a perpendicular there, just accept it. Rectangle gets set up. Sorry that I can't prove it for you here. Okay, so this is 140 degrees. But if this is a rectangle, that takes up 90 degrees here. Okay, so inside of this angle right here, this has got to be 90 minus, well, 180. Jeez. The whole thing is 140. Okay, right? This whole thing is 140. Look, 140. How did I get that again? A nonagon's interior angles, they're each going to measure 140 because it's regular, right? And each regular, like, equiangular, we can figure it out, right? Using the formulas that we studied back in chapter 2 or chapter 3. But anyways, what I'm going to do here is I'm going to do 140 minus the 90-degree angle that was right here. It's going to tell me that this is going to be a 50-degree angle. Ah, nice. Okay, so we have a right triangle and we have a reference angle in there. And there we go. So we can take this group's word for it, but hey, they got the 50-degree reference angle. They end up solving for it. They got it good to go. Let me show you the trig involved in solving it here, because this is right triangle trigonometry now, this problem. This is right triangle. We have a right angle there. This is a 50-degree reference angle. This is x, right? So here's our opposite side, and we know our hypotenuse, right? Our hypotenuse is just going to be any side length of the regular 9gon, so it's 25 millimeters. So let's go ahead and set it up, and mathematically, we will get it there. So opposite over hypotenuse, that's so, right? Sine ratio. So we're doing sine of 50 degrees equals x over 25 millimeters. Okay, what am I doing? Sine of 50, and I'm going to multiply both sides by 25 millimeters. So I go 50, and I hit sine, there we go, times by 25, and I'm going to get 19.15, okay? So x equals 19.15, but wait, that wasn't the answer that they got, or it should be approximation. Is approximately equal to, because they got this. How did they get that? Well, right, we got to add on that 19.5 there, and this other one was x here. We got to get what this whole thing is, okay, right? This is AD. This is what we're trying to solve for in this one here, okay? So I'm going to do, right, this is 19.5 right here. This is 19.5 right here. So that means AD has to equal 19.5, which we just solved for has got to be that side, right? This is, again, a 50-degree reference angle. I use the sine ratio to get x, plus 25 millimeters, plus 19 point, for the millimeter part here, plus 19.5 millimeters, and that's going to give us our answer. And we're going to get that same answer that they got as soon as we add that together. I might just do times by 2 there, and then plus 25, and there we go, 63.3. So excellent work here, group 6, getting through the answer. And thank you to whoever asked. I can't tell who asked these questions there on the parking lot. So thank you for asking that here. Hopefully that helped out a little bit here too. That was kind of a tough question. I wouldn't expect anything quite that complicated on a quiz or anything like that. So excellent work there. Take care, guys. Ask more questions. I love hearing them, and it definitely helps you, I think, too. All right, thanks. Bye.